Hi everyone, this is the first video from section 8 where we're going to start talking about power series. And in a way, the rest of this chapter, sections 8 through 11 of chapter 11 that we're going to do, you can kind of think of these as some of the interesting applications of these sequences and series. Because I know up until now they probably seem a little bit abstract, but it turns out they're actually really useful for doing a lot of practical things. Some of it will still be just pure math, but some of what we're going to do forward will actually be some nice applications. But before we get to the application, we still need to do a little bit more background mathematics. So we're going to talk about power series, and you can kind of think of these as we're going to use series, the concepts thereof, to define interesting real functions. So here's the basic definition of what a power series is. So a power series really is basically a real value function like we were studying kind of in the first half of the semester. You plug in a real number, you get out a real number. But it's defined in terms of some series. So notice I've started with n equals 0 here rather than n equals 1. That's what your book does. Most of the time I'm going to try to match that unless the particular series we want to look at is not defined for n equals 0. Something like that. But we're going to go with n equals 0. The reason is so that the first term is just a constant. So this gives us an infinite series like this. And so notice these CNs are potentially all different. It's kind of boring if they're the same. We can talk about that example in a little bit. But a couple other pieces of vocabulary, the CN. So Cn is what we call the sequence of coefficients. Because if you look at this thing, it's basically a polynomial, except in a polynomial, the rule is you have to stop at so many terms. You have a degree of it. But no, this just keeps going on forever. So the power series is basically like a polynomial with infinitely many terms. So not technically a polynomial, but very similar. Okay. So when we have the sequence of coefficients that we go with them. So let's do but we know with series, a series could potentially diverge, which is not good. So the domain of any such power series so anytime you have a function defined by a power series, the domain of that function is only the values where the thing actually converges. Okay. So anywhere where this thing diverges, that's not gonna be part of the domain here. So I'm gonna do a quick example to kind of get this under our belts. So an easy example is what I started to mention a minute ago. What if the coefficients were all just 1? Well, that just gets us the sum of x to the n, which is a geometric series. We know particularly when that converges. We know that converges for everything between -1 and 1, and it diverges for everything else. Therefore, this function f of x is only defined for -1 to 1. And we know what this sums to. And remember, geometric series always sums to a over 1 minus r. So here, your radius r is actually your variable x. The a is the coefficient on it, which is 1. So in particular, this gives the function 1 over 1 minus x, the perfectly valid rational function that we could have talked about in the first half of the semester. We probably did at one point, maybe. You can represent that function in terms of a power series. And that becomes very powerful. Being able to take a potentially complicated function and represent it as a sum of some polynomials, be able to, if I took this series and just stopped it at the 10th, at n equals 10, and just had the partial sum for n equals 1 to 10, that ends up being a really good approximation for this function. And for complicated functions, having a really good approximation to that function that's just a polynomial ends up being really helpful. So that's part of what we're building towards in this second half of this chapter. Okay, so that's a pretty easy example. So I should mention, though, that there's a little caveat to this definition that I really haven't mentioned yet, and I should. So this series this power series here that I've drawn right here, that is said to be a power series that is centered at 0. Okay, why is that phrase meaning? What I'm going to do now, I'm going to rewrite the definition to include this vocabulary about a center. So a power series is said to be centered at A. A is just going to be some number here. So in general, you can have a power series with this kind of representation. So you still have a sequence of coefficients. It's just instead of x to the n at each entry, you have x minus a to the n. Because notice if you take this series and plug in x equals a, you get the same thing as you would for this series with plugging in 0 for x. So this becomes important. Sometimes when eventually the goal of this will be to try to take a function like this and find a power series representation for it. That representation could be different depending on where you want to center it. So that's just a little bit of what's the literary term? Foreshadowing. There it is. That's a little bit of foreshadowing of why this concept is going to be important. That will be coming in the next section, though. All right, so with this vocabulary now, okay, so this is really the better definition for what a power series is. It's a power series centered at a particular number. A lot of times we're going to center it at 0 just because 0 is a nice number. It's easy to do arithmetic with. It's important. But sometimes you want to center it away from 0. And we want to be able to have vocabulary to express that. Okay. I want to now do an example of a power series that's more complicated than this one and see exactly when it's defined. Okay. Okay, so this time we have a power series defined by the sum from n equals 0 to infinity of n factorial times x to the n. So I just like to write down a couple. When I see this, my instinct is I want to realize where the power series is being centered. It's not x minus anything, so it's really x minus 0 if you like. So this thing is going to be centered at 0. And I also like to just identify remove the x to the n or x minus a to the n part and identify what the sequence of coefficients is. So I don't have space to write it fully away to the side, but yeah, the sequence of coefficients is just the sequence n factorial. Okay, so notice here we have both a factorial and a exponential. So both of those types of functions lead me to suggest that if I want to determine the convergence of this for a particular value of x, the ratio test is going to be one to use. Because the ratio test is really good for dealing with factorials and especially exponentials. Exponentials, as you can see, they're going to come up a lot in these power series. So the ratio test will be the most common test we use for this type of material, this section anyway. Okay. So I do realize we kind of have two variables competing for our attention. We have x and we have n. So obviously for x equals 0, if x equals 0, then this definitely converges. Everything is 0. If you sum up infinitely many zeros, you get 0. So this definitely converges for x equals 0. The idea is here, when I'm looking at the series, I want to pick a particular value of x. And then, so I'm going to fix x. X is no longer being imagined as a variable in my eyes. It's a fixed number now. And I'm looking to see what the convergence is for just the summation variable n. Okay. So, in fact, if I fix x to be any number besides 0, we know what happened to 0, just talked about that. If x is any other number besides 0, let's look at the ratio test. Remember, for the ratio test, we set up the limit as n goes off to infinity of the n plus first term over the nth term. And the numerator here is the n plus first term. The denominator is just the nth term. Okay. And remember the absolute values. Absolute values are important. N we know is positive because it's heading off to infinity and it's starting at 0. But x could be negative. I'm just assuming x is a real number of some kind that's not equal to 0. So x could be negative, so I do want to make sure the absolute values stay on the x's. Okay, but the n's I know are positive, so I don't need to worry about it there. Remember, a property of the absolute value is that you can separate it with that it's multiplicative. By that I mean what I'm going to write here. And if I have a product inside of absolute value, I can separate it into this product. So I'm going to do that. I'm going to pull everything with the n's and the factorials. And when I do that, that part's not going to need absolute values anymore because everything's positive. Remember, n plus 1 factorial over n factorial. Remember, n plus 1 factorial will be n plus 1 times n factorial. So I get cancellation happening. And all I'm going to be left with is n plus 1. Oh, I feel like I went through that quickly, so I'm going to write that out a little bit more slowly. So I have this. I just separated the parts. And this part didn't need absolute value bars. This part still did. Okay. I've run out of space and I need to erase. So I'm coming over to this side of the board now. All right, so as I was mentioning a moment ago, n plus 1 factorial over n factorial. N plus 1 factorial is just n plus 1 times every positive integer less than it, so that's just n factorial. And then this n factorial will cancel with this n factorial. And I'm left with n plus 1. Inside here, remember your rules of exponents. X to the n plus 1 over x to the n. That will simplify to just x, actually. Remember, it's still in the absolute values, though. So n is my variable that I'm letting go to infinity. X is, I'm kind of fixed x as some specific number that's not 0. And then absolute value of that is at least positive. Absolute value is always of either positive or 0. And since x is not 0, absolute value of x is not equal to 0. So this limit here is infinite. So this example ends up being kind of dumb. Because if x is not equal to 0, by the ratio test, this series diverges if x is not 0, which isn't too hard to see that, because I have n factorial, and I'm not dividing by it. N factorial is just going to make this blow up to infinity pretty quick. No matter how tiny x is, n factorial is going to go to infinity quicker than x to the n is going to go to 0. So this is going to blow up. So I already discussed that f of 0 equals 0. If I plug in 0 for x, this converges to 0. But by the ratio test we just did, the series diverges no matter what else x is. So this function is kind of dumb. It's only valid for x equals 0. So not terribly interesting. I did this example even though it's not ends up terribly interesting, just to show you the procedure of how we think about power series, how if we're given a power series, it's always of interest to us to learn when exactly it converges. And so therefore when the power series function is actually defined. Okay. That's what we're going to get at in the next this video and the next couple videos. So this is actually where I want to end this video, because we've got a couple more interesting examples and a couple results to share in the next video, and that's going to take a little while. So I don't want to have this video go on forever. So for this video, that's all we got. And again, in the next video, we'll have more interesting examples. All right. If you have any questions about this definition or anything else, write it in the comments or message me. And thank you for watching.